Right now, as you are watching this, there is a volcano on the floor of the Caribbean Sea that scientists cannot see and cannot hear. It sits 8 kilometers north of Grenada. It rises 1,300 meters off the seabed. Its summit crater is 300 meters across and roughly 197 meters below the surface of the water, close enough that a container ship passing overhead has no idea it is there. And its official alert level has never, in the entire history of its monitoring, been allowed to drop below yellow. Not because it is always erupting, but because nobody can confirm that it is not. Its name is Jenny. It is the most active volcano in the Eastern Caribbean, and when it produces an earthquake swarm, which it does without warning sometimes hundreds of events in a single night, the response is not what most people would expect. Scientists do not primarily run earthquake models. They run tsunami models. Because the danger from this thing was never the eruption. The Caribbean Sea records roughly 15,000 earthquakes a year, about 40 a day of magnitude 1 or greater, 33 of magnitude 5 or greater annually, and at least 56 above magnitude 7 since 1900. Swarms are routine there. This one is not routine, and by the time we're done here, you'll understand exactly what makes a swarm on the seafloor a fundamentally different problem than a swarm on land, why the volcano's summit is deeper today than it was in the 1970s, and the single sentence on the monitoring agency's own website that should stop you cold. Today, we are going to break down exactly what is going on, where it is most dangerous, and whether things could get even worse. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever personally been on a boat, a ship, or a coastline when the water did something it should not have done? Tell me where you were and what it felt like. I read every single one. If you want to be the first to know every time something major happens, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one so the algorithm actually shows it to the people who need to see it. Now, let us get into it. Let us start with what a Jenny swarm actually looks like when it happens, because the numbers escalate faster than almost anyone expects. The most recent well-documented episode began at around 10 in the morning on August 27th. By 8 o'clock the following morning, roughly 22 hours later, the University of the West Indies Seismic Research Center's monitoring network had recorded approximately 800 tremors, 800 events. Overnight, beneath a single volcano. The largest of them measured between magnitude 2.2 and 2.4. That is small. That is genuinely, unambiguously small. Small enough that not a single person on Grenada, 8 kilometers away, reported feeling anything at all. And that is precisely why this is not read the way a land swarm is read. Through the following day, the activity began to decline. Between noon on August 28th and 8:30 in the morning on August 29th, the network recorded 72 events, an average of 3 to 4 per hour, with the largest in the magnitude 1.4 to 1.8 range. Over the weekend, the rate dropped further to 1 or 2 tremors per hour. By August 30th, the volcano had returned to background activity. Throughout the episode, the Seismic Research Center issued a series of advisories to Grenada's National Disaster Management Agency. The alert level remained at yellow. The maritime exclusion zone remained unchanged at a radius of 1.5 kilometers. Nothing happened. The swarm came, peaked, and faded in about 72 hours. That is the outcome the overwhelming majority of the time. Hold on to that, because we are going to come back to it at the end, but it does not always resolve that quietly. In July of an earlier unrest episode, the pattern ran differently. Signs of elevated seismicity began on July 11th and continued for nearly 2 weeks, with more than 200 micro and small earthquakes recorded over that period. Then, between 1:25 in the morning and 3 o'clock on July 23rd, instruments monitoring the volcano registered a strong, continuous signal. Not discrete earthquakes, but sustained tremor. The alert level was raised to orange. Orange, on the 4-color scale used for this volcano, means a highly elevated level of seismic or fumarolic activity or other highly unusual symptoms, and explicitly, that an eruption may occur with less than 24 hours' notice. At 2 o'clock the following morning, July 24th, the instruments recorded an hour-long explosion event. Scientists conducted an overflight on July 25th to look at the water above the volcano. They observed nothing out of the ordinary at the surface. By 6 in the evening, no further activity was being recorded, and on July 26th, the alert level was lowered back to yellow. An hour-long explosion at a volcano, 197 meters underwater, and from an aircraft directly above it, the sea looked completely normal. That changed fast, and it is the single best illustration of the core problem with this volcano. To understand why a seafloor swarm is treated differently from a land swarm, you have to understand what monitoring this thing actually involves. Jenny is a basaltic andesitic submarine volcano in the Lesser Antilles Island arc, formed by the subduction of the Atlantic plate beneath the Caribbean plate. On land, a volcano gives you an enormous amount of information for free. You can see steam, you can see ash, you can measure gas chemistry directly from a fumarole, you can put instruments on the flanks, on the summit, in the crater, you can watch the ground deform in real time with satellite radar. Underwater, all of that disappears. The monitoring network, the Seismic Research Center, operates for Kickham. Jenny is genuinely sophisticated, and it is worth describing precisely because it shows how hard the problem is. It includes seismometers to detect earthquakes, tide gauges to detect disturbances in the water, hydrophones to detect submarine explosions, and tilt meters and GPS stations to detect ground deformation. Various combinations of those instruments are installed at Sauteurs on northern Grenada, on the Sisters Rocks, on Isle de Ronde, on Isle de Caille, and on Carriacou. Their signals feed to a small base station at Sauteur, and from there they are transmitted onward to Trinidad. Every one of those instruments is on an island. None of them are on the volcano. There are no permanent seafloor instruments. The detection of submarine activity relies substantially on regional seismographs picking up what are called T-phase signals, acoustic energy from an underwater event that travels efficiently through the ocean sound channel before converting back into a seismic signal at a coastline. So when 800 events arrive in a night, scientists are not watching a volcano. They are inferring a volcano from a distance through water using instruments planted on the rocks and islands around it. And here is the part almost nobody outside the region knows. Because scientists can neither see nor hear this volcano directly, the lowest alert level for Kickham Jenny is yellow. There is no green. The exclusion zone of 1.5 kilometers around the summit is to be observed by maritime vessels at all times, not during unrest, at all times. Now, to put that in context, why does any of this rise to the level of running emergency models? Because the hazard from Kickham Jenny is not primarily the eruption, it is the flank. A submarine volcano builds itself by piling erupted material around its own summit. That is how every volcanic island in the Lesser Antilles began, growing slowly upward from the seafloor until it broke the surface. But volcanic material accumulated underwater is loose, steep, waterlogged, and structurally poor. It is stacked at angles that would not hold on land. When magma pushes into an edifice like that, it does not just risk an explosion, it risks destabilizing the entire slope. And a large volume of rock sliding off a submarine volcano into deep water displaces an enormous quantity of water very suddenly, which is the exact recipe for a tsunami. The scientific literature on this specific volcano reflects that emphasis directly. The foundational hazard papers by Smith and Shepard, published in the early and mid-1990s, are titled around tsunami waves generated by volcanic landslides and preliminary investigations of the tsunami hazard of Kickham Jenny, not the eruption hazard, the landslide tsunami hazard. There is also evidence written into the volcano's own shape. Between the 1960s and the late 1970s, the depth to the summit was measured at approximately 180 to 190 meters. Today, the summit is estimated at about 197 meters below the surface. The volcano is deeper now than it was 50 years ago. A volcano that erupts repeatedly should be building upward. When the summit gets further from the surface instead, material has been removed through crater collapse, through slope failure, through the redistribution of the edifice. A research cruise in 2003 mapped the neighborhood in detail and identified 3 craters, designated C1, C2, and a feature called Kickham Jack, along with 2 domes. This is not one simple cone. It is a complex, repeatedly rebuilt, repeatedly failed structure. That is what the models are for. When the swarm starts, the operative question is not will it erupt? It is the slope moving? Now let us talk about what that means for the people who live within reach of it, because this is where the numbers become human. Kickham Jenny sits directly on the shipping route from St. Vincent to Grenada. The waters around it are heavily trafficked by cargo vessels, inter-island ferries, fishing boats, yachts, and cruise ships. The Caribbean is one of the most cruise-dependent regions on Earth, and the small islands nearest the volcano, Grenada, Carriacou, Ile de Ronde, the southern Grenadines, have economies built substantially on the water. In 1939, Kickham Jenny erupted in a way it cannot currently repeat. It broke the surface. That eruption generated waves. The volcano is now considered too deep for that specific style of surface-breaking activity. The water column above it suppresses the explosive interaction that produced the 1939 display. But depth cuts both ways. Being deeper protects against a surface explosion. It does absolutely nothing to protect against a landslide. If anything, a taller, more built-up, more deeply submerged edifice has more material available to fail. And now, the sentence I promised you. The Seismic Research Center's own published description of the Kickham Jenny warning system states its purpose plainly. The main purpose is to provide warning to shipping in the vicinity. It is not a tsunami warning system. Read that again. The monitoring network around one of the most active submarine volcanoes in the Western Hemisphere, a volcano whose primary documented hazard is a landslide-generated tsunami, exists principally to keep boats out of the exclusion zone. The agency is not hiding this. They publish it. They are being scrupulously honest about what their system can and cannot do, which is exactly what a responsible scientific body should do. The system is designed to detect premonitory symptoms before an eruption begins, and to let scientists judge whether activity is building toward a stage where a tsunami could be generated, with the expectation that vulnerable communities would then be given warning to move to higher ground. But the distance between "we may be able to judge that a tsunami could be generated" and "an automated system will alert every coastal community in time" is the entire gap in this story. The regional precedent is not hypothetical. In 1918, an earthquake in the Mona Passage generated a tsunami that killed on the order of 100 people along the coast of Puerto Rico. The Caribbean is not a place where tsunamis are theoretical. It is a place where they have happened, and where the coastline is now vastly more developed than it was a century ago. So, what are scientists watching now, beyond Kikumjeni itself? The first thing is the instrumentation gap. Everything about the current system is a workaround for the absence of permanent seafloor instruments. Seafloor pressure sensors, cabled observatories, and ocean bottom seismometers exist and are deployed at monitored volcanoes elsewhere in the world. They are expensive, they are difficult to maintain in a corrosive marine environment, and small island states with limited budgets have not been able to install them at scale. Closing that gap is the single highest value improvement available for this hazard, and it is a funding question far more than a scientific one. The second is the wider Caribbean plate boundary, which is genuinely one of the more complicated tectonic settings on the planet. The Caribbean plate is a relatively small plate wedged between the North American and South American plates, subducting on its eastern edge beneath the Lesser Antilles Arc, which is what built Kikumjeni in the first place, and grinding laterally past its neighbors to the north and south. The northern boundary is the reminder of what that system can produce. In January 2020, a magnitude 7.7 earthquake struck the Cayman Trough on the Septentrional Orient Fault Zone, at a depth of about 15 kilometers between Jamaica, Cuba, and the Cayman Islands. It was strike slip, so it produced only a modest tsunami, about 46 centimeters at Georgetown. There were no casualties, but the shaking was felt strongly enough that buildings were evacuated in Miami, and light shaking was reported on the Yucatan Peninsula, a magnitude 7.7 on the Caribbean plate boundary, emptying office buildings in Florida. Keep an eye on the Lesser Antilles Arc more broadly, too. Kikumjeni is the most active volcano in the eastern Caribbean, but it is one member of a long chain of subduction-built volcanoes running from Grenada up to the northern islands, a chain that has produced significant eruptions on land within living memory. The arc is active along its full length, and keep an eye on how these advisories are communicated. Throughout the August unrest, the Seismic Research Center repeatedly pushed the public toward its own verified channels and those of the National Disaster Agency, a direct response to the reality that a submarine volcano swarm generates enormous quantities of social media speculation within hours, most of it wrong, some of it deliberately alarming. So let us close this honestly, because the honest version matters more than the frightening one here than almost anywhere. Kikumjeni is not about to destroy the Caribbean. The August swarm produced 800 small events and then stopped. The largest tremor in it was a magnitude 2.4, not felt by a single person on Grenada. The alert level never rose. The exclusion zone never changed. Within 3 days, the volcano was back to background. That is what these swarms almost always do. Submarine volcanoes and active arcs produce seismic swarms as a normal part of existing. Magma moves, gas exsolves, rock fractures, and instruments record it. A swarm is evidence that a volcano is alive, not evidence that it is about to fail. No one can predict volcanic eruptions or the timing of a flank collapse, and the Seismic Research Center does not claim to. The Orange Alert episode is equally instructive in the opposite direction. An hour-long explosion was recorded, the alert was raised, an aircraft flew over, the sea was undisturbed, and within 72 hours the level was back to yellow. The system worked. It escalated appropriately and stood down appropriately. But here is what is real. The danger is not the volcano waking up. The danger is the shape of what we would know if it did. There are no instruments on Kikumjeni. There is a 1.5-kilometer circle drawn on a nautical chart to keep ships away, and a network of seismometers planted on the surrounding islands doing an admirable job of inferring what is happening in the dark. And the agency that runs it states, in plain published language, that this is not a tsunami warning system. 8 kilometers to the south is Grenada, and a wave born on that seafloor would not need 8 kilometers of ocean to cross before it arrived. It would need about as long as it takes to read this sentence. Drop a comment below and tell me, did you know there was an active volcano under the Caribbean shipping lanes? Have you ever been on the water when something felt wrong? Tell me where you were and what it felt like. I read every single one. If this taught you something you did not know about the seafloor, hit the thumbs up. We are going for 5,000 likes, so the algorithm shows this to the people who most need to see it. Subscribe if you want to be first to know every time something significant happens. Let us go. See you in the next one.